Okay, we will start. Okay, so now few things about the little bit more about the basic electrochemistry. This will be probably the last but one or last class or last presentation on the basic electrochemistry. Generally, we used to only use the metallic electrodes. Why are we using metallic electrodes? Why are we not using other things as the electrodes? Is the question we have to ask. Now, you know very well that mercury is used one of the electrode materials, but it has a certain drawbacks, even though it is very commonly and also advocated for certain specific measurements like the polarography and all those things where you need a fresh surface being exposed every time. Okay, but mercury being a liquid typical material, but it is a liquid, therefore constant elevation of atoms on the surface in contact with the solution. Therefore the electrodes are not really talking about the uh, uh, stationary electrode. Okay, the atoms are changing and all those things are there. So therefore generally that is the reason why the people are using the solid electrodes. Now when we are using the solid electrodes, why are we using metals? Why are we not use other electrodes is the question you can one can ask. We'll come to it later. In the case of the metals, the redox potentials are well defined functions. In the case of other materials, depending upon how you have prepared it and how you are doing it, the the distribution of the electrons or the Fermi Dirac statistics applied to these systems are different. Therefore in those cases, uh, the definition or the defining of the potentials will become a problem. We will be dealing this a little later when we are dealing with the uh, other electrodes later on. So now if I were to look at this, so when we use the metals, it can be monocrystalline or polycrystalline metal sheets, metal rods, metal whatever it is. In solid metal electrodes, the conduction is mainly due to the movement of the free electrons. Because we are talking about metals, we already talked about it. And the electrons at the Fermi surface or Fermi energy or Fermi surface is the correct thing because of the three-dimensional situation. So therefore uh, the Fermi energy is an important parameter. So now if I were to take the Fermi energy, then look at the electron distribution. It is given by here F is equal to 1 over 1 minus 1 plus exponential E minus EF by KT. This is the Fermi Dirac distribution, where K is the Boltzmann constant, EF is the Fermi energy, E is the energy of any energy value given that. Fermi energy therefore corresponds to electrochemical potential of the electrons in the metal electrode. When E is equal to EF plus KT, okay, then F will take a value of, if you are approximately calculating it, will be 0.27, and when V is equal to EF minus KT, okay, not KBT, Boltzmann constant, then F will be equal to 0.73. The variation of F with energy is shown in, we are going to see that picture now. You can see the variation of F with respect to, F means the distribution function with respect to energy is given here, with respect to energy is given here. Energy is given here and F is there. You see F remains constant at this value when E is equal to EF. That is, this is the value. Whereas when T is equal to a particular value T1 and T2, the distribution, the density of the occupied states in a metal in the region of the Fermi energy at T is equal to 0 and T is equal to 1 and T is equal to 2, where T2 is greater than T1, T1 is greater than T0. So you can see this is T0 or T0 is equal to 0. When it is 0, this is the distribution function. When it is a definite value of T temperature, it is this distribution. So this is what is the problem there. Okay, so therefore occupancy will be sharply decreasing at EF, while high temperatures the occupancy is smeared out. I hope you have seen that occupancy is dying out like this, whereas as we go on towards the T0, it becomes all places at the Fermi energy is present. So now quickly looking at it, by convention for a metal, only electrons with energies within kT of EF can be transferred. That is why we always use this expression E minus EF by KT, and also that is why we use E is equal to EF plus KT, or E is equal to EF by minus KT. So therefore only those electrons very near to the EF alone will be transferred. The interfacial structures of a solid electrode are of various types. Okay, the interatomic distances vary with the exposed crystallographic planes. Therefore the transfer also is a function of the planes, even though we are conventionally looking at it as a, say, simply metallic electrode, but it is not so. In a polycrystalline material, one can have various kinds of defects, and these are also can give rise to a distribution of the electrons. Absorption of the species can also be changing the electron distribution. The absorption can be specific or non-specific. So now the structure of a double layer associated with the interface of monocrystals with the solution has been investigated in a variety of metals like gold or gold or platinum. Now, as a clear difference between crystallographic phases is noted, we have already talked about it. We said that the electrochemical behavior of the metals with the different crystallographic planes will be different, as manifested in the values of differential capacity and the evidence of adsorption in voltograms. In the specific adsorption can be there. This is a well-known thing in adsorption phenomenon. We will come to it later on. That is why iron 111 is more active for ammonia synthesis than iron 100 or iron 110. Cyclovoltograms, we have to think about the cyclovoltograms in a very great detail. I will do one lecture on cyclovoltograms themselves, and then what all the things that can be done with cyclovoltograms. Suggest that there is a reorganization of the metal surface to give equivalent of a surface layer of lower Miller index. Okay, I hope you understand. There is a reorganization of the surface in the electrolyte medium. The identity of this phase depends upon the applied potential. Potential also, the potential also is one factor responsible for the reorganization. The identity of this phase depends upon the applied potential. These studies are still in their infancy. We have to spend some time on this, how this potential is going to be responsible for the reorganization, whether it will be also giving rise to this. This is one thing that is not very clear in electrochemistry. For example, when we take a metallic electrode, we assume that it is a metal, but the surface could have got oxidized because of the potential. We'll see later on. Okay, this is what is called restructuring of the surface. So we have to look at this and then understand the electrochemistry that is taking place. So now quickly looking at it, the effects of the crystallographic phase and the difference between different metals are evident from the incorrectness of the classical representation of the surface interface with the universal type of potential decay within the solution. For example, the same copper cannot be the same in two electrolyte medium, or even with the two different situations in the same electrolyte medium, but it may not be same because the dissolved oxygens may be different. In fact, a discontinuity at the interface is improbable. It should be a continuous function, and the experimental evidence shows that the variation of the electrostatic potential with the distance may deviate from the value in the bulk electrode even at a certain distance from the interface inside the electrode, as is usually called done in the Jellium model. What we have been assuming is that the potential drop is only in the solution phase, or the interface starts from the interface to the electrolyte phase, but it may not be true. It may be penetrating a layer thickness or something like that, but this is more predominant in the case of the other materials, semiconductors and others, whereas in the metals it may not be, because in the metals there is a Jellium model. Therefore it will be, even though there is a small difference in the electrostatic energies of the electrons, they will be smeared out. This corresponds to therefore we have to look at these two models differently. The chemical models reflect the fact that the electrons of the solid penetrate a tiny distance into the solution. Okay, due to the wave properties of the electrons, the wave functions at the interface will be more or less similar to the wave functions of the wave functions of the electron in the electrolyte and the wave functions of the electrons inside the electrode in the metals. But this will be very small extent or so to a very small depth in the electrode. It will not be very deep in the electrode. So now quickly looking at this, in this treatment, the galvanic or inner electronic potential associated with the EF and the volta outer electron potential, that is a potential outside the electrode electronic distribution approximately at the inner Helmholtz plane 10 to the minus 5 centimeters from the surface are distinguished from each other. I will show you a picture and tell you. The difference between these potentials is called the surface potential. Maybe we'll take a picture of that, then only we'll be able to understand this. So I hope you are able to see the galvanic potential is this, the potential of the electrons inside the semiconductor. The volta potential is the potential of the electrons inside the in the electrolyte, but very near to the electrode. So the difference between these two potentials, galvanic potential and volta potential, is called the surface potential. And in the electrolyte, the potential drops and goes to the minimum value as the distance away from the electrolyte. Okay, so I hope you understand this. This is what is happening in the case of the applied potentials. So therefore, we have to necessarily understand what is the way the potential is varying with respect to electrolyte, because we all our fuel cells are going to be in this sense only. So therefore we have to necessarily look at the potential variation with respect to electrode, electrolyte, and also inside the inner Helmholtz plane, inside the outer Helmholtz plane. So we have to think all of them together. In the semiconductor electrode, we will be having a different situation. Okay, we have been doing this in a number of times. Okay, we will simply look at it only once, then only we will understand that. So in the semiconductors, you will see that, I hope you are able to see in the electrolyte. If I will assume that the electrode is positively polarized, therefore negative ions will be more in the inner Helmholtz plane or diffuse double layer with respect to the positive ions. Whereas the positive charges are if it is were to be metal electrode, it will be very thin layer. Whereas in the semiconductors, it is penetrating to a depth of this. All these things we have seen number of times, so we will not spend much time. We will see later on how to calculate all these parameters. So now quickly looking at other aspects of this. So semiconductor electrodes also, you see, I have put some numbers, but we will not worry at this point. In isolated atoms which are characterized by filled and vacant orbitals that are assembled in a lattice containing 5 into 10 to the 22 atoms per cubic centimeter, new molecular orbitals form. These are all very tricky situations we will see later on. So therefore, the bands are separated by forbidden gap. I hope this is already known to you. I will take a picture and show it to you. This is what is happening. Okay, this is the filled orbital in a isolated atom or metal, whatever it is. Then as I go on in the internuclear distance and go to the metallic state, this levels spread like this, gives rise to an occupied band. The same way, the vacant orbital also spreads like this. Therefore, there is an overlap of the valence band and the conduction band in the case of the metal. So now, the moment you go to the semiconductors, you can see that this is the top of the valence band and this is the bottom of the conduction band. So there is a gap that is there. So now, if the semiconductor were to be here, you can see that this is the gap. So therefore, in the isolated atoms, if the occupied state, in the bulk metals, it is overlapping. In the semiconductors and insulators, they are not overlapping. So this is the picture. This how to generate this picture and things we will see little later or in separate presentations on solid state materials. Okay, we will see later on. Maybe we may have to do a course on solid state materials later on. So now, if that is the case, what is happening is the question. Okay, so this is what is happening. The bands are separated by forbidden region or band gap of energy Eg, which has the unit of electron volts. When Eg is very much greater than kT, or when the conduction band and valence bands overlap, the material is a good conductor of electricity. If the Eg is very much less than kT, then they are overlapping with each other. When the Eg is greater than kT, then it is a semiconductor. So by conversion, if the separation is greater than 3 electron volts, then it is called as greater than 3 electron volts, it is called insulator. If it is less than 3 electron volts, it is called semiconductors, and if it is 0, it is called metals. Okay, so this is I already shown, this also I already shown. So quickly looking at it, in a semiconductor electrode, the accessible electronic levels are restricted, and this has important consequences. Promotion of an electron from the valence band to the conduction band leaves a hole, a lack of an electron and a positive charge. It is therefore essential to consider not only electron movement but also hole movement. Here there is a migration of both charges. Conduction occurs by movement of electrons in the conduction band and of holes in the valence band. So this is all the pictures that you have seen. This is the valence band. So this is the forbidden gap. So you in the normal circumstances, this is the A is a typical band structure of a valence semiconductor in the two-dimensional model. Please to think that this is a two-dimensional model. This is not a three-dimensional model. Okay, three-dimensional model will be slightly different. So when the occupancy of the positive ions and negative electrons are equal, then the Fermi level will be exactly in between the conduction band and valence band. If the impurity levels were to be very near to the conduction band, then the Fermi level will be very near to the conduction band. If the impurity levels were to be very near to the valence band, then the Fermi level will be very near to the valence band. All these things you would have studied some point or other. We will also deal with this separately in a different situation. So the intrinsic semiconductor electron promotion to the conduction band occurs through thermal or photon excitation. Whereas in the normal semiconductors, where the band gap is greater than 1 or 2 electron volts, the only photons can do. This is photons can preferentially do. Okay, you can do with the temperature also. This is defined as the energy level at which the probability of occupation of the electron is half, is called the Fermi level. We have already talked about all these things, so we will not worry at this moment of time. So now, in terms of the band gap, we have already talked about it. So therefore, the number of excited electrons in a given situation will be equal to n will be proportional to exponential minus Eg by 2kT. We now consider what happens at a idealized interface between semiconductor electrode and electrolyte. This is a separate topic which we are not going to do today, but we simply look at some pictures. So now you can see that this is the potential. So the potential now, if you remember the potential which we saw here, you see the potential within the electrode is not changing at all. Whereas here, I hope you are able to see, the potential changes within the solid as well as within the liquid. So therefore, this is the potential drop within the solid. This is the potential drop at the interface, and this is the potential drop with respect to inner Helmholtz plane to the bulk liquid. Okay, so this is what is the potential situation with respect to the electrodes. So now the same situation I have shown here with respect to the semiconductors. Now what is happening here is this, that this is the energy levels of the substrate. I hope you are saying the redox system. Now you will understand why we are worried about the redox system. So the electrochemical electron transfers are going to take place at the interface through the redox system. Okay, depending upon whether the levels of the redox system is overlapping with the valence band or overlapping with the conduction band, then that species will undergo reduction or oxidation. So therefore, the energy level, for example, you look at here, the valence band is here, and the the redox potential is here. Therefore, the electrons are not capable of going from the valence band to the conduction band. Whereas if the electrons were to be in the conduction band, the unoccupied states in the metal is going in the redox system is going to be here. Then the species will undergo reduction. So therefore, you can see easily that from the knowledge here, why we are showing this by not an individual energy level but a band. Okay, here also we are showing a band because there are so many redox species at the interface. At the interface, the redox species is a concentrated situation. So you should not call this band, but it is number of available redox species. That is why it is shown. And each one of the energy redox species will have energy levels spread out a value, because each one is in under the influence of another redox species. That is why instead of showing it as a one single level, we are showing it as a number of levels. But it is all of average energy only we are going to consider. So if we consider the average energy, we can say that only those reduction potentials which are very much above the valence band will not undergo reduction. Therefore, only the electrons from the conduction band will oxidize the substrates. Whereas if this is to be, for example, in this case, you take the reduction potential and the valence band is similar. Therefore, the holes can migrate here, or the electrons can go there. Therefore, they can undergo oxidation or reduction simultaneously. So this presentation is mainly for showing you what will happen if the electrodes, for example, we are in a fuel cell, we are going to look at the dipping an electrode, or dipping is not correct, inserting an electrode in an electrolyte medium. So therefore, how the electron transfers are to take place is what is being done. So I will stop at this point and answer any questions that you have. You have any questions? Hello. Okay. Best of luck.